Good morning, everyone. So this is third lecture. The order of things got a little bit exchanged with respect to the program, so sorry about that. But sort of just summarizing very briefly, the first lecture we went over together sort of the basic idea behind the concept of trying to simulate or trying to perform quantum field theory simulations using various kinds of systems. Okay? We've been focusing on optical systems, but we also went through the fact, sort of described other kinds of systems we've been talking about. Yesterday we were talking about VCs. We're also talking about fluid analogue, so using flowing water. And we also went through, in the first lecture, we went through sort of like the basic mathematical tricks that you can use to sort of calculate how a space-time varying background can give rise to photon flare production. Okay? So what I want to do today is provide you with, show you another set of analog systems. And I think there's also an interesting question hidden here. I mean, I'll just be showing you how you can use light in a different way from what we saw yesterday. Yesterday we were talking about very short pulses moving down a fiber, for example. Okay? And there, the analog model was working in the co-moving frame with the soliton or with the laser pulse. Okay? Today I'll be talking about an analog that works in the lab frame. And I'll show you how you can use light to make, for example, rotating black holes or simulate the Newton-Schrodinger equation. But there's another underlying question, we'll come back to that later, as to whether these fluids that I'm saying, so the title here, fluids made of light. So I'll be using light to create an analog, but the question for you at the end will be, are the fluids that I'm making, are those real fluids or are those also analog fluids? Okay? Let's go a little bit through the details first. Okay? So the setup, and I'll show you a picture of this later, is actually extremely simple. All you need is some kind of nonlinear medium, which I'm showing this like this glassy thing here, okay? And the CW laser beam. So it can be very cheap, very inexpensive, extremely simple to build, and very accessible. Now, I won't go through the whole derivation of this equation, but it's sort of well known that in the nonlinear optics regime, the propagation of the electric field is described by this equation here, which you can see looks like a Schrodinger equation, but has this term here, this nonlinear interaction term. Okay? So this is called the nonlinear Schrodinger equation. Okay? This is just derived directly from the Maxwell's equation, with including this nonlinear term in the polarization. Okay? Now, what you can do is you can take this equation, this is what it's got a fancy name, it's called the Madelung transform, from the name of the guy who did this the first time back in the 1920s, but I mean, it's not really a transform. You're just substituting, you're just calling E the square root of rho, which I'll call a density, and you'll see in a moment why I want to call this the density, times E to the I phi. So I'm just saying that the electric field is an amplitude with a phase. Okay? So there's nothing strange in there. And then if I also do these substitutions, which may look a little bit weirder, but we'll come to that in a moment. So I call the gradient of my, essentially there's a constant here, but what I've got is the gradient of my phase. I'm going to call that V, hinting at the fact that that's going to be a velocity. And I substitute T with Z, okay? Now if I do that, and I plug this, essentially I plug this into there, and then I'll see that these gradient terms will pop out, and so every time we do it, I write V instead of the gradient of phi. I end up with these equations. And you can see here, I don't know if you recognize these or if you've seen them before, but here I have a continuity equation for my density rho, and here I have Euler's equation, okay, which describes the evolution of a fluid. In other words, what I have here is a set of hydrodynamical equations for the density rho and the phase, this phase phi. Okay. And so the density here, or in other words, so what I've got this mapping. So so here you have some references where you can find more details about this, in particular the papers by Chow think we're some of the first to sort of really sort of pinpoint how to show that light behaves like a fluid. Okay. Now there are a couple of points here. Let's have a look. So this is sort of a more detailed version of what the sort of the setup looks like. I've got a tube filled with some material, and then I'm going through the material here. Now I said I'm going to swap T with Z. Okay. So each plane here along the Z direction corresponds to a different time in my propagation. Okay. This, by the way, this transformation here is only related to the fact that I've chosen this kind of material. There's another version of these photon fluids where you put everything in a cavity. So I'd have a mirror here and a mirror here. Then when you go through the maths, you start from a slightly different equation, respect to nonlinear Schrodinger equation, because you need a term in there to account for the fact that you have a cavity. When you do the transformation, you find this Madelung transform, you find out that actually T remains T. Okay? So this is just a little bit of a technical detail, but it shouldn't worry you that T has become Z, because actually that's quite natural in the nonlinear Schrodinger equation. Now we have our speed, which is proportional to the gradient of the phase, and we can identify a speed of sound in our material, which is just given as proportional to the square root of the delta n. Okay, the same delta n that I was talking to you about yesterday. N2 times intensity or times power. Okay. The other point that I didn't sort of underline when I was writing this equation is there's a minus sign. Now, in typical materials, the sign of the N2 of your curl third order nonlinearity is positive, which means that as you send in your beam, there would be an attractive, you can effectively see it as a photon-photon interaction. We spoke about this during the first lecture. You'll have an attractive photon-photon interaction. The beam will tend to collapse. But in order to create a fluid, that's not what you want, right? If you think of, what is it that distinguishes a fluid? Well, it's made out of molecules, and the molecules tend to repel each other. Okay? You need a repulsive photon-photon interaction if you want to make a fluid. And therefore, you need a negative, you need a minus sign there. You need a negative N2. Okay? So that then forces you to choose very carefully exactly what material you put inside this tube. Okay? So you need to make sure that you have the right sign of your N2. Okay? So the way you should think of this is you've got this very long sample sending a beam. You've got some transverse beam profile, so which we identify, remember, the square root of rho is E, is the amplitude of E, so rho is E squared. So the amplitude of the beam gives us the sort of the density profile of our fluid. And then what we're looking at when I talk about the speed of sound, okay, I'm not talking about real sound here. By speed of sound, that CS parameter, okay, this guy here, is referring to the speed at which little waves move on the surface of this beam. Now, I don't know, I don't know if any of you have actually seen a theoretician when he draws a laser beam will draw something like this, okay? So this is putting radius here and intensity, for example, okay? But that's not how a real laser beam, so this is what I would identify as being the density, okay? But that's not what a real laser beam looks like, okay? A real laser beam always has some imperfections on it, okay? And it's these imperfections, these waves, if you want, that I'm talking about here, that I should identify with sort of like the waves on the surface of a pond, okay? And then, of course, I've got sort of, this is the front view of my beam, okay? I'm looking at it. There'll be sort of imperfections all over the place. But now I hope you can immediately realize that I can actually control the shape. I mean, I can either just study what happens with these random sort of imperfections, noise, okay, spatial noise on top of the beam, and I can try to analyze those. Those would correspond to like the noise that you see on a pond. But I can also create waves very simply. I can come in with another beam at an angle and create an interference pattern. Okay? That interference pattern will represent effectively a wave, that has a wavelength given by the periodicity of the interference pattern. Okay? So seen from the top, this is my sample. I'm coming in with sort of the big pump beam here. So it's got some thickness to it, okay? And then what I can do is I can come in with another beam at an angle, and there will be an interference pattern here, okay? And just by changing the angle, you can change the wavelength of these waves on top of my fluid, okay? So let's have a look at a bit more detail at what kind of samples we've been using, what kind of samples you can actually use. So again, this is sort of the simplest form of the layout. We'll see more later on. They will get a little bit more complicated. But essentially, this is it. And you just need the CW laser. We've been working, people usually use 532 nanometers with 5, 10, or 15 watts, simply because there's nothing special about this wavelength. It's just it's a very widely, and I'm holding one in my hand, it's a very widely available laser, okay, and relatively cheap. And you just shape the beam, you try to clean it a little bit, and then you just send it through your sample, and then you have some imaging system, some filters, and then you just image directly the profile of your beam that exits the output facet over here, okay? Now, what's inside here? Well, what we've been using is we've been using a thermal nonlinearity. So the idea is, so in here we've been placing various kinds of liquids, but typically we'll just use methanol, for example, okay? And the idea is that the laser beam, a small portion, so you don't want to have huge absorption. You want to have, for example, across the whole length of our sample, we have typically something like 10, 20% absorption, not more. But that small amount of absorbed light heats the medium, okay? And the idea is that all materials have a refractive index that depends on temperature. They have a thermo-optic coefficient, okay? And now you can choose, and I say you need to be careful about the material. A lot of materials, for example, most glasses, have a positive thermo-optic coefficient. So if that's the profile of my beam, it means that the delta N will do something like this, okay? What we want is a negative delta N. So you go, but there are liquids, there are also glasses, but there are many liquids that have a negative dN in dt. So this is the number that you get. So methanol, for example, for every Kelvin, for every increase 1 Kelvin in temperature, I get a change in the refractive index of the order of -4 10 to the -4, okay? So here's delta N will look more like this, which is exactly what I want, okay? The higher the density, the larger the repulsion force between photons, or the larger the photon-photon interaction. Okay? Now, in order to, methanol itself does not absorb very much. Okay? If you just send your beam through pure methanol, you'll have less than 1% absorption. So that means you'll have a tiny change in refractive index. In order to increase that a little bit, what we've been doing is been dissolving graphene nanoflakes into the methanol, okay? Other people typically use dye. You can use rhodamine dye, for example. So rhodamine is a fluorescent dye which absorbs in the green and re-emits in the red. It's very common in most laser labs. The reason for using graphene, in our case, well, there are two reasons. First is rhodamine, it's a dye, so it gets all over the place and stains stuff. But also you're not transforming, if you think about what's happening, you are not transferring all of the absorbed energy into heat, right? Most of it, it's fluorescent, so most of it is you're absorbing at 532, and you're re-emitting at 650-ish, whatever. So if you do the maths, it means that sort of something between 60 and 80% of the energy that's absorbed is actually being re-emitted at 630, at some other wavelength, okay? And then the rest is going into heat. In graphene, on the other hand, there's no fluorescence. Everything that's absorbed goes directly into heat. So you need, let's say you can get, for the same amount of light absorption, you can get a larger temperature increase. So a more efficient way of doing it. Okay, and these graphene nanoflakes, you can buy them in solution. They cost nothing. You get a bottle this size for something like $200. Okay. So this is what the system actually looks like in the lab. Here you can see I'm coming in with the laser beam. There's a hologram here. We'll come back to that later on, why that's needed. Then we've got a collimating lens. And here, I don't know if it's obvious from this photograph actually, but this is just literally a piece of plumbing from waterworks. Okay, we just took a piece of copper tube and with copper rings on the front and just put some windows there, and then we can unscrew them and change the material inside whenever we want. Okay, so it's a very cheap and easy to build do-it-yourself setup. Okay. Okay. Now there is a subtlety in all of this. I drew a beam like this and kind of said, hand-wavingly, that that's the delta n, kind of implying that the delta n might follow the same profile as your beam, okay? But that's not what happens because this is a thermal nonlinearity. It's based on heat, and heat diffuses, heat moves around, okay? So I can have a beam which is delta thin, but the heat will diffuse outwards. So my heat profile actually looks something like this. What that means is, so when you say the nonlinearity is non-local, it means that areas over here can affect what happens over here. Okay? So what you need to do is you need to account for this because it's not trivial. It's not obvious that you want it. And I'll show you some examples today where you do want it, but there are also cases where actually it really does get in the way and you need to learn how to harness it and control it. Okay? But the first thing you need to do is you need to go back to your equations and you need to account for this non-locality. And the way you do this is you essentially have to, your delta n is no longer n2 times intensity, okay, or power, but it's now a convolution integral. It's a convolution between your response function, which essentially tells you, given a delta excitation, how does heat spread out in the material? Okay, so you convolve that response function with the profile of your intensity profile of your laser beam. Okay, so things become more complicated now. You've got a differential equation, the Nonlinear-Schrodinger equation, that contains this integral term. Okay. Now, the typical response function for heat sort of diffusion is this form here. It's got a known function. It's not something, although we did go, and you should go and measure it, and you can check, but it has this sort of like exponential dependence. But so if you plug that in and then try to sort of mathematically calculate this, you can ask yourself, so what does the non-linearity, the non-locality actually do to the delta n? Well, the result is that instead of having a response like this, you get something that looks like this. It spreads it out, okay? But the most important thing, so it reduces a little bit the amplitude, but the most important thing is that it spreads out the interaction. So photons over here can feel what the photons over here are doing. Okay. Now, this does have implications. Now, if we go all the way back to these equations here, and these are the equations of an ideal fluid, and if you can pull out from these hydrodynamical equations what is called the Bogoliubov dispersion relation. Okay, I don't want to go into the details of where this comes from, otherwise we won't have time to look at all the other things. But essentially, this is a dispersion relation, so it links omega, the frequency of your waves, with the k vector of your waves. Okay, and essentially, so you have a term here which scales quadratically. So this is squared. This is to the fourth power. So if I just take a square root, it means that this term here. So there's a quadratic scaling with k. Okay, this is what is often called quantum pressure in the superfluid community. Okay, it's due to the fact that at some point you have the particles or the components of your fluid cannot stay too close together. There's a repulsion force. In optics, this just very simply, we also have this term. It simply corresponds to the fact that you have diffraction. So diffraction, the natural diffraction of your beam, is essentially a quantum pressure term. Okay? It's just different wordings for exactly the same physics. Okay? But it is the same physics. It's not mimicking. So we have kind of it is a quantum pressure. It's just that in optics, you don't talk about quantum pressure between photons. But it is the same thing. Why does a beam diffract? A beam diffracts essentially because of the uncertainty principle, which is precisely the physics that lies at the base of quantum pressure. Okay? Then you have this other term. This is typically sort of a new term. This is the interaction term, okay, which forces the photons to interact with each other. And this, you see now, scales linearly, okay? So let's forget this term for the moment. If this wasn't here, this would mean that I would have, if in the region for the region of k values, so typically for small k values, where this dominates, I'll have a linear dispersion relation. So my omega k will just be a straight line, okay? And this is a typical feature of superfluidity. They have just a straight line for your dispersion relation. So in other words, what it means is I can pull out here the speed of sound or the speed of my waves is constant. There's no dispersion. For any omega, any k, all the waves propagate at the same speed, okay? And then for higher k's, this term starts to dominate and it becomes quadratic again, okay? So this is sort of the curve, the kind of curve that you get with, should be delta n less than 0, sorry. And you have zero non-locality, okay? And, oh, sorry, but I forgot to mention. So this length here, there's a specific length where you have this transition from linear to quadratic, comes on this usually called the healing length. And this region in the middle here is where you have superfluid behavior, okay? If I have zero delta n, so there's no interaction between the photons, I just have my purely quadratic dependence, and there's no superfluidity at all. So the whole fluid is just dominated by this quantum pressure term or by fraction, depending on the words that you want to use. And then there's this sort of region that we'll be working in where you have an interaction, the delta n is different from 0, but you also have this sigma is what I'm using to characterize the width of the diffusion, okay? The width of my diffusion response function. And what you see is there's a region here where I'm still linear, I still have a superfluid behavior, but now it's become a lot smaller than what I had before. Before, my superfluid behavior extended all the way out to these k vectors. Now it's restricted to roughly k vectors that are of the order of 1 over sigma, okay? So this non-local length is now limiting the region of superfluidity in my system. So this is already have an example here of where non-locality can get in the way. If you want to study superfluidity using these photon fluids, well, then you're in trouble, because if you have a very small, or let's say, so if you have a large, non-local length, then essentially the superfluid region will be cut off and can become very difficult to access. Mm-hmm. It's interesting you ask that. So we don't know. I'll show you in a minute. I thought it was the next slide. I'll show you in a minute a slide where I think we do, but we haven't been able to nail down where it comes from, why it's there. I think there's a detail in the shape. So it really, the short answer to your question is it depends on the shape of that non-local response function. So if that response function decays, for example, has a Gaussian shape, so you know, mathematically go to MATLAB and put in any number you want and just calculate what happens here. So if you put in a Gaussian function, so something that decays very quickly, then indeed you find that in this transition here, so essentially what's happening, you can see this dashed curve is transitioning from my superfluid behavior to the linear behavior. It's going from this black curve to this orange curve, okay? Now, whether I see a roton or not depends on how quickly I transition from the black one to the orange one. So if I transition relatively slowly, you can see there's no roton here. But if I make the transition very abrupt, then you can see that in order to get over here, it could very well be that I do something like this. And in our measurements, it seems that this is exactly what is happening. But then on the other hand, that does not seem to be in agreement with the actual kind of response function that we went and measured. So there's something else going on there that we haven't quite nailed down yet. It's an interesting question. So, Rich, following up on your question, the first thing you want to do when you've got a new kind of fluid is you want to characterize the omega K dispersion relation, because that really tells you, it gives you a lot of information on how your fluid is behaving and how waves propagate in this fluid. Okay, is it a superfluid? Is it just a non-fluid? Is it just this linear behavior? What is it doing? Okay, so we came up with two different techniques. The first one is not fully legitimate, but I think it's still very interesting. What we did was we just took inspiration from what people do in oceanography. So there are papers out there where people have been taking satellite images of the ocean, okay? It's a series of images, and they can measure. You can see, you can either see actually waves, you can either pick up the waves, or you can just look at the sort of the noise that is always present on top of the ocean surface, in very much the same way that a laser beam always has some noise on top of it, okay? And you just measure the evolution of this noise over time, okay? And then what you do is, so you'll have a series of X and Y, so 2D, and time, so 3D images, okay? And then what you can do is, for example, you can just take a line out, so you have X and T, it's a two-dimensional image, and you do a two-dimensional Fourier transform. So the X will go into K, and the T will go into omega. And so that's a very neat and interesting way of pulling out the omega K relation from a very simple Fourier transform. Okay? And you can do the same thing here. So what we were doing was, we were just, you've got just some natural noise. These are actual pictures, by the way, of the beam. So you can see the noise here. It's been sort of exaggerated a bit in the color scale, but you can see this noise on the beam, and you just take measurements at different planes inside the material that would correspond to time, and then you just take a line out along here, and that would correspond to your spatial dimension. Then you do a 2D Fourier transform. Okay, so that's what kind of concept I'm trying to point out. And all we're using is just sending a beam. We didn't pay any particular attention to cleaning it. We wanted to keep the noise in there so that we could use that to populate our omega K curve. And this is what we get. So you can clearly make out here sort of like these parabolic shapes, okay? And what we're doing is the difference between these three graphs is that here the velocity, the mean velocity of the fluid is 0. Here it's 1.3 10 to the 6 meters per second, and here it's 3 10 to the 6 meters per second. How did we control this speed? Remember, the speed I said is proportional to the gradient of a phase, of the phase of the beam, okay? So if this is, let me redraw this. So the setup I showed you earlier on, I just had the sample, I had the beam coming in, and then I had some imaging optics and the camera, okay, CCD camera, watching what's happening at the output here. So this would correspond to the case where I have 0 flow in my beam. Now, if I want to increase the flow, I just need to I want a linear flow, okay? So I want a constant speed across the beam. That means I need a linear phase profile across my beam. So if these are the plane wave fronts for 0 velocity, if I want a linear phase inclination, so if I get a constant speed across the beam, that means I need to somehow tilt the wavefronts, okay? But what that means is tilting the wavefronts, well, that's very easy. I just come in at an angle, okay? So you just slightly tilt the angle of your beam. Note, by the way, that everything's relative, so you don't necessarily have to tilt the angle of the beam. I can just tilt the angle of the imaging system, and I'll get exactly the same effect. Okay? So it's by controlling this angle here that I can control the speed at which so from that angle, I can calculate what the phase is, and I can calculate what the speed is. Okay? So there's no interference pattern here. Well, I guess you could consider these as interference patterns of lots of, so this noise, you can consider as coming about because I have on top of the beam lots of plane waves going in all different directions, creating interference patterns. And that speed there, that V there, is the speed not of these guys, but of the beam of the fluid as a whole. It's like having a pond. That's the first case, just a lake sitting still, nothing's moving, or I have a river. So everything's moving. So there's a river moving with fluctuations on top of it. Yes. Okay? Okay? And what you see is, if we go back to the, oh no, it's here, this Bogoliubov relation, you see that the speed enters here. Okay? So I've got omega minus Vk. So if let's neglect this term for a moment, put this to 0, you have omega equals essentially k squared. So you just have a parabola. But if I now start increasing the v, I'm going to put a linear term on top of that parabola, so the parabola is going to start to tilt. And that's exactly what you see here. Okay? So I start to increase the speed, this tilts, this is a perfect parabola, this starts to tilt a little bit, this is tilting more. Okay? And we were able to see that these parabolas with so there's no free parameters in these bits. Okay? We're just pulling out what the speed is from the known angle and then placing it on top of these graphs, and the fit was perfect. Now, you might notice that I was talking about parabolas. There doesn't seem to be in these graphs any evidence of this nonlinear term playing a role. Remember, this nonlinear term should give me superfluid behavior, should see a straight line. And here, all I see is just parabolas. What's going on? Well, there's something which I didn't mention here, is that what we're doing is we're trying to, so how did I get the different imaging planes inside the material to actually do this, then do this Fourier transform? Well, what I did was I simply translated, I kept this distance fixed, and then I translated the imaging system and the camera back and forth, okay? So I was then directly, instead of imaging this output plane, I was imaging directly inside. Now that usually is okay. It requires a little bit of care because the refractive index in this region is different from the refractive index here, so that's going to change your imaging a little bit. But the key point here is that that's the system, the whole point of doing this, because this system is nonlinear. And you're not allowed to do imaging inside a nonlinear medium, okay? You can't just take a linear imaging system based on lenses and nothing else and try to image inside the nonlinear medium. And when I say not allowed, you can do whatever you want, but the answer is not going to be correct. It's not going to give you a proper image of what you have inside. Now, there are tricks to do this. There's a very nice Nature paper, Nature Photonics, I think, by Jason Fleischer, where he says, well, actually, you can image inside a nonlinear medium. What you need to do is when you hit, so for this region here, what you have to do is actually have to back solve, you have to backward propagate through the nonlinear Schrodinger equation in order to factor out the effect of the nonlinearity. So these wave equations, you can propagate forwards in time, but you can flip. You can send t into minus t and propagate backwards, okay? So you take the image here, you propagate backwards using the full nonlinear Schrodinger equation, and you can pull out an image of what you have in here. But that's what you have to do, okay? A lens, what a lens is usually doing is it's solving for you the linear propagation equation, okay? But it can't solve the nonlinear one. You have to do that with a computer. And what is happening here is essentially, remember I said that, and you can do that, although no one's done it yet, but we're looking into it. You can also do it for the non-local nonlinearity. But that's not what we're doing here. And remember what I said, the effect of the non-local nonlinearity is to smear everything out. And that's exactly what we're seeing here. I mean, we've lost all details, sort of the fine details of the dispersion curve, because we smeared everything out. Yeah? Oops. You're talking about this guy? Or you're talking about this guy? Mm-hmm. Sure. So you have a branch here, you have a branch here. So what I'm plotting here is just the positive branch. Here. So there's an intersection over here. Yes, there's also an intersection, and it still be here. Okay, so the curves. So were having some discussions yesterday. This is the positive frequency branch. This is the negative frequency branch, okay? Dispersion relations are always of the form omega squared proportional to k squared. So there are always two branches, positive and negative frequency one. And they will also, in this case, oops, terrible drawing. In this case, you're exaggerating a little bit. They'll be touching here, okay? This is a reflection of the Fourier transform. Again, that's an artifact of the Fourier transform. So you have to be very careful. We tried to remove it by putting some kind of Gaussian or super Gaussian envelope on top of this. But if you take, whenever you take, so if you take a Fourier transform of this, you'll get a Gaussian. But if you take a Fourier transform of this, so I've truncated it at the edges, that's going to add in sort of like a sync kind of modulation, okay? And that's what you're seeing here. Okay, those are just artifacts. Okay, so that was curious, interesting, kind of worked, but it didn't really pull out the fine details. What we were really interested in seeing is if there's a superfluid behavior or not, okay? And we need to do something better than this oceanographic technique. So what we did was essentially a pump and probe technique. So we did exactly this. So we now have a beam going straight forward, okay? And what we're doing is we're sending in a very weak probe beam. This very weak probe beam will now, so I've got, let's say, a close to perfect pump beam that's creating my fluid, and then I'm sending in a probe beam that will create a small oscillation on top of this beam. That's what this will look like, okay? And then what I'm looking at is how this probe beam moves. What's this? I want to directly measure the speed of that probe beam inside my fluid. Okay? And if I do that for lots of different, I can keep on changing the angle, meaning that I will change the wavelength of this beam. Okay? So I can map out in my K space. If I measure the speed, if I know what the K is, because I can measure that, that's just the wavelength of the interference pattern, I can measure the speed. Well, then I can map out this curve here. Okay, so that's the essence of the experiment. The way you do this is you take this is the input pattern, okay, look to this very low intensity, and then you crank up. So there's just a linear medium, so it won't be propagating, and then you crank up. So that's your reference wave. Essentially, it tells you where the wave is located at the input. Then you crank up the power, and you look at where the wave is at the output, okay? And you'll see it shift due to the fact that it's a wave propagating in a fluid with a certain speed. The distance here, essentially, is what I'm calling delta S. It's a difference in where the waves are located, divided by the time it takes to go from here to here, gives you the speed of that wave. Okay? So if you do that, here I'm just plotting out the shifts that we actually measured versus the wavelengths of our waves. Okay? And we find something like this. This is the curve that we'd expect if we had a local nonlinearity, and this is the curve that we actually predict in the case of a non-local nonlinearity. So you can clearly see, so over here the two curves come together, but down here you can clearly see the deviation due to the non-locality. Okay? But the interesting bit is, remember when I was, this will be the next graph, but remember when I was drawing the dispersion curves, when they're similar, that's because you're in the superfluid regime. Okay? And you can see that there's a region here where indeed we have a series of accessible wavelengths where we see superfluid behavior. Okay? So in more detail, going back to sort of the more familiar omega k graph, these round circles are our experimental points, and you can see that we have a very nice superfluid behavior in a series of wavelengths that are actually experimentally accessible. Okay? And coming back to your question, we remeasured these points, I don't know how many times, but lots, because I thought they were a mistake. And I told the student to go back and remeasure again, and then remeasure again, and it doesn't go away, it's there. So this would seem to correspond, you know, and I said it's all about how you transition from the black curve to the orange curve. Well, here, this transition does seem to be going through a Roton minimum. Can I, as in you're asking if I can make this deeper? We didn't try. So the answer to that question is I don't know. Maybe. Okay. Okay, that's something we could look at. Interesting. Okay. Okay, so you can find more details. How much time have I got? Oh, time's running out. Okay. So you can find more details about this in this paper that we published last year. Okay, so we then wanted to go and double check that against the, here, these measurements allowed us to pull out a sigma, a non-local length, and the value of the delta n. Okay, the value of the delta n is what we expected, but what about the sigma? Is it correct or is it wrong? So there are other ways to directly measure this response function, okay? You can hit a thin sample of your liquid with a very small beam, like exciting it with the delta function, and then with a bigger probe beam, you send that through the material, and then you measure at the output the phase distortions on that beam, and that will allow you to assess directly what the response function is, okay? So this is a measurement technique that was sort of introduced by Minovich and co-workers in this optics letters paper in 2007. Now, if we do that, so we measured the non-local length of 120 microns, okay? But with our oceanographic or whatever techniques you want to call them, but then when we do this, when we directly go and probe and look at just the sigma, well, what we find actually is something very different. We find a sigma which is of the order of 1 centimeter. So this is the measurement, and the dashed curve here is the actual numerical simulation of the heat diffusion equation. So we have two things. We have a numerical simulation of a heat diffusion equation, which we all believe to be true, okay, and an actual experiment. And these two are in very good agreement, telling us that actually the sigma is way larger. It's 1 centimeter, and that just happens to also be, for very good reasons, and I'll come to that, happens to be half the diameter, or the radius, if you want, of the tube that's containing our sample. Okay, so what's going on? Well, the trick, there's a point, something which I didn't point out here. The beam we're using here is highly elliptical. Okay, and that turned out, at the time, I can't remember why we did this, but that turned out to be a lucky coincidence, and we learned quite a lot from that. So, whereas here, this measurement was done with a perfectly round beam. So what's going on, and how is it that the geometry of the beam, or is it the geometry of the beam that's influencing this? Well, the solution is indeed that there's an interplay between the geometry and the non-locality. So the beam, so we definitely know that the sample geometry will modify your non-local length. If you have, and this is simply because when you solve the heat equation over here, okay, if you solve it numerically, you have to explicitly put in the boundary conditions. And then you have to decide what the boundary conditions are. So do I put the delta T equal to 0 at the boundary, or there are various choices you can make. But what we took was that these are the boundaries, then whatever, no matter how hot it is in the middle, it has to go, this heat change has to go to 0 at the boundaries. Because then you're essentially, when you think physically what you're doing, you're hitting a copper tube that's in contact with air, and so the heat will be very quickly dissipated. Okay? So you can easily see then that if I make the sample larger, the sigma will become larger. If I make it very small, the sigma will be small. Okay? So that's relatively trivial, the fact that the sample geometry can modify the non-local interactions. What is less trivial, I think, is the fact that the beam shape can do exactly the same thing. And the underlying idea here is that if you have a highly elliptical beam, So this dimension is roughly equal to size of the sample, but this dimension is much, much smaller, then you'll have a huge heat flow in these directions, and that will essentially therefore behave or give sort of an effective boundary that reduces the non-locality in all directions. And you can show this, we came up with a model that kind of supports this. So what we did was, the first point is that if you want to come up with a model that supports this, you want to be able to do some analytical calculations. You cannot solve this equation analytically with the boundary conditions. You can only do that numerically. Okay? So how do we account for the boundary conditions in this equation, yet still be able to solve it, provide some kind of analytical solution to this heat diffusion equation? Well, what we did is we added this additional term here, which is essentially a loss term for heat. Okay? So so this effectively accounts for the fact that although this equation does not see any physical boundaries, what it does see, though, is it sees a loss of heat, sort of uniformly distributed across the whole sample. Then you try to mimic this, use this to mimic the fact that you have heat loss going out through the boundaries. Now, this can be solved analytically just by going to the Fourier domain, and this is the response function you get, this kind of Lorentzian function, okay? And if you then take a Fourier transform, a 2D Fourier transform, remember we have a 2D fluid, then for this response function, it gives you something like this. This is the zero-order modified Bessel function, which essentially still has this exponential decay. Okay, and this is the same plot that I showed you before. This is the numerical, the blue line is the numerical simulation with the proper boundary conditions. The red curve is the measurement, and this black curve is us plotting this analytical solution to what we call this distributed loss model, okay? And you can see that it fits perfect. Of course, it's not, you see that the numerical simulation, as I was saying earlier on, has to go to 0, because that's the boundary condition that we put. It goes to 0 at the boundaries. This guy doesn't. As far as he's concerned, the boundaries are infinity, okay? But this distributed loss gives him exactly the right shape, at least in the center. It's wrong here, but everywhere else, actually it's working extremely well. And most importantly, it's working well in the region where we want it to work well, here in the middle. Okay. So I won't go through too much of the details here, but essentially this is just then justifying if I do take a highly elliptical beam, if you go back to this guy, that means that these KYs are going to dominate. They're going to be very small Y direction. That means these KYs are going to be very large compared to these guys. So I can throw these guys away. And then that means that essentially the whole dynamics, or the heat dynamics, is dominated by this term. It's dominated by the size of the beam. And that's where the geometry of the beam comes into play. And so that's this kind of approximation that I'm making here. So essentially what I'm saying is that the sigma, the non-local length, is actually given by the diameter, the smallest diameter of the beam. And indeed, that now agrees extremely well with our experiments, because we measured 130 microns, and the beam was 120 microns wide. So this model fully accounts for the way heat is flowing in the system. Okay? So I went a little bit through these details to sort of show you sort of all the kind of physics problems that you encounter, sort of the interesting sort of discoveries that you can make, just trying to build something new. But essentially, the bottom line is that by acting on the beam geometry, we can restore superfluid behavior. Remember, the sigma, the natural sigma of the system, was 1 centimeter. Okay, so that would mean if I go and look at my, dispersion relation, let's draw it out fully here. Okay, I was saying it was something like this. Okay, and I was saying that normally I have this whole region here is superfluid. Then I say, but when you have a non-locality, it's decreasing. Okay, so but if I say that I've got a material that has a radius of 1 centimeter, and the cutoff length for superfluidity is also 1 centimeter. Well, aside from the fact, it means that the superfluid region here becomes super tiny, But most importantly, it means that the only way to observe superfluidity is to put waves in that have a wavelength larger than 1 centimeter. But that would be larger than the sample itself. Okay, so I can't fit a single wave into my sample that would actually behave like a superfluid. So in other words, although in principle there could be a region of superfluidity here, but given the fact that I actually have boundaries, I will never be able to access it experimentally. So this ability to control the non-local length is extremely important. Without it, we would be lost and all this exercise would be useless. Okay, there's another way to, I'll go through this really quickly. There's another way to control the non-locality, and that's by looking at how the material responds in time. By time here, I mean real time. You switch on the laser beam, and of course, heat doesn't diffuse instantaneously. It takes a while, okay? So this is the radius, this is the temperature map. And as you switch on, I mean, it starts from 0 temperature difference, and then as you wait, so the time scale here is typically of the order of tens of seconds, okay? And then the heat, you start heating the system, and then it starts gradually, the heat gradually broadens out. So I could do some measurements over here, where you can see still have quite a good temperature difference, so therefore good delta N, but the non-local length is much, much smaller than it is over here. So these are actual measurements. We did measurements by just using a camera that's triggered now, so we're switching the laser beam on and off, triggering the camera, and then measuring over various time intervals, and measuring the delta N, and you can actually see this delta N increase in amplitude and spread out as the heat starts to spread, okay? But the interesting thing is that whereas over time, this is bilogarithmic scale now, whereas over time, the delta N actually doesn't change by too much, okay? Here it's only changing by a factor of 3 or 4 at most. The non-local length actually changes by 2 orders of magnitude. So in other words, it allows me to choose a relatively large delta N, because it's not changing much, but I can go wherever I want along here and choose the non-local length that I want without changing much the delta N. Okay, so if you work, for example, at around 20 or 200 milliseconds after you switch the laser on, you've got a tiny sigma, you're nearly got a local material, local response, but you still have a relatively large delta N. And that's how we're doing everything I'm going to show you from here on. That's essentially how we're doing these measurements now. We switch on the laser, and the camera takes a picture 200 milliseconds afterwards, okay? So, for example, let's go back to our elliptical beam. And we said that by using this elliptical beam, we can restore superfluidity. Is it true? So one of the hallmarks of superfluidity is that if you make the superfluid flow around an obstacle at low speeds, you will see no waves. This is very different from a flowing body of water. You stick your finger in, you see waves. A superfluid is viscousness, there's no viscosity. It doesn't generate waves. But if you increase the speed and you go above what is called the Landau critical speed, you will generate turbulence and waves. And in particular, you'll generate quantized vortices. So it's this spontaneous nucleation of quantized vortices that is usually considered one of the hallmark traits of superfluidity, okay? So we used an obstacle, so we had to use sort of an extended obstacle like this. This is just a knife blade, and it has to be present for the whole, it has to be a long knife blade because remember Z is equal to T, okay? So we want it to be there for all times, so it means it has to be there for the whole length of the sample. So this is essentially what it looked like. We had the blade, and we just had our elliptical beam coming in at an angle, therefore creating the flow. And by increasing the angle, you can increase the flow speed and go and see if you actually create and nucleate vortices, okay? And so these are numerical simulations, just to check what's going on. The beam is flowing from left to right. This is at very low powers and nothing particular is happening. This is amplitude and phase. The nice thing of these superfluids, main difference in spectra BCs and superfluid helium, is that we can measure the phase. And that's a really important feature when you want to go and try and look for vortices, because as you can see here, when we increase the power, the vortices will appear as a 0 in the intensity profile, but most important, and that can sometimes be a bit tricky to to sort of pinpoint. But most importantly, they appear as a phase singularity. You see this fork pattern in the phase here, which tells you that you have a quantized vortex. Okay? It's quantized because when I go around in a circle here, I do a whole 2 pi turn in the phase. Okay? So, oops, why did that stop? Okay, so these are 2D simulations based on nonlinear Schrodinger equation. There you can see I just nucleated a vortex, and I'm about to nucleate another one. Okay, and this process will just keep on going. Okay, and so these are the measurements. Again, you can see in the phase profile, you can see very clearly the edge of our obstacle. This is the intensity, and you can see these zeros. They look exactly the same as what they look like in the numerical simulations. Most importantly, when you go and measure the phase, I won't go into the details of how we did this, but essentially it's just an interferometric technique. You just re-interfere your output beam with the reference beam. You can pull out the phases, and you can see that here, at relatively low speeds, I nucleate just one vortex. If I have a higher flow speed, then I manage to shed off 2 different vortices. This is sort of a blow-up of that image there, showing you the detail of the vortex. Okay, so this kind of really proves that our fluid is behaving as it should. It's a superfluid, flows around an obstacle at high speed. It sheds off quantized vortices. Okay, so yes. Yes, so we published this in a PRA, this work in a PRA paper. And interestingly, what we found is, I don't know if it's obvious from this, or maybe a bit more obvious from here, the vortices have this elliptical, they're elliptical. Usually people they're expected to be round, okay? Here, they're elliptical, and this ellipticity arises, so we've got a plot there where we plot for various working conditions. So the both axes of these ellipses. And this is arising from the fact that you have, it's essentially arising from your non-local non-linearity. And what's happening is, remember I was saying that the different photons here affect what photons are doing over here. So as you're nucleating the vortices from the edge of this knife edge, instead of nucleating, you can see this actually quite clearly. They're not nucleating from the tip. They're nucleating from a bit further down. And this is due to the fact that the non-locality is spreading out the potentials, the nonlinear potential that is creating these vortices. And it's spreading it out. This is an extended edge. So it's extending it out along this direction here. And that is why, ultimately, why you end up with an elliptical. You can see the ellipsoids are sort of directed along this direction. It's why you end up with these ellipsoidal vortices. I can't remember the exact numbers. We can go and look at them in the paper. Of the order of tens of microns. They're big. And compared to superfluid helium, where you're talking nanometer scale, these are readily visible. Okay, this is just a camera without any particular enlargement. So to give you an order of magnitude, actually, I can tell you, to be more precise. This is a knife blade, and sort of this region here is about 100 microns wide. So that allows you to see immediately sort of the order of like a few or 10 microns. Okay. Okay, so why are we doing all this in the first place? I mean, all of this was just gearing up to just prove what kind of fluid we have and how it behaves, and just check that it behaves like a superfluid. Why am I interested in the fact that it behaves like a superfluid? Well, the point is that if I have a linear dispersion relation here, then this essentially is something that I can use to mimic the light cone in relativity studies, okay? If I have something which is wobbling all over the place, has huge dispersion, I'm in trouble. Remember yesterday I mentioned, talking about the optical analog, that there was a big thing that I just swept under the carpet, which was that actually all materials have dispersion. And if you take a material with dispersion, it turns out that so your n depends on omega. It also means, in other words, that it depends on time. And that prohibits you from being able to write out a proper space-time metric. Okay? And we kind of ignored that yesterday and did it anyway. But if you want to do things properly, you want to be in a system where there is no dispersion, so that when you write out a metric, that is a real metric. It's something you can really use as mathematical well-defined. And so that's why we're interested in building a superfluid. So once you can do that, you can, these these papers by Francesco Marino, for example, that are published in PRA 2008, 2009, you can take your hydrodynamical equations where you have the superfluid behavior, and you can write out this, you can rewrite the wave equation for those waves, and you can pull out a very nice metric, okay? Where this V0 is the speed of your beam, and you have CS again, which is the speed of sound in the material. And you can only do this because that is a number. It doesn't depend on frequency, it doesn't depend on time. Okay? So then what do we want to do? What can we do here that we couldn't do before? Well, it all comes down to this. So the key point is yesterday, everything I spoke to you about yesterday, all the papers I mentioned, all the work done so far before this in analog gravity was all 1D, okay? So you can only build a 1D black hole with everything that I've mentioned up till now. But now I have a 2D, I have a two-dimensional superfluid. So I can create a two-dimensional black hole. Okay, so what would be the difference between 1D and 2D? Well, in 2D, I've already shown you that I can spontaneously generate vortices, okay, quantized vortices. Well, in 2D, what I can simulate is a spinning black hole, or what is called a Kerr black hole, okay? And there's a lot more physics in a rotating black hole. As soon as you add rotation to your system, there's a lot more interesting physics you can do. And what we're interested in at the moment is this idea that was first introduced by Roger Penrose, not in 2002, this is just a reprint of his paper from 1969. And go and read it. It's a beautiful paper, and it's this beautiful drawing drawn by Roger Penrose himself. He's got a very characteristic way of drawing things, is contained as part of the discussion in that paper. And essentially what he's saying is, well, you've got a black hole here, which is rotating. Okay? These are your Minkowski light cones that he's plotting here. And he's saying, well, imagine that there's some alien civilization that builds some kind of huge scaffolding that surrounds the black hole. And they want to use the black hole to extract energy and then survive using this energy that they can extract out of that. So how would you go about that? Okay? So the obvious thing, one thing you could do, is you could have this is sort of like a long piece of rope attached to a spring, okay? And you attach a mass to the end of this piece of rope, and you just lower it into the black hole, okay? And as you approach just outside the event horizon, you let go of this mass, it will get sucked into the black hole, and the spring that will be released will give you an energy, which in the ideal case up here will be equal to E. You'll have E equals mc squared. So it will give you back the same amount of energy that was contained in the mass that you just dropped into the black hole. He said, great, that's one way. But he said there's an even cleverer way where you can get even more energy out of the black hole. He said, now assume, let's come a little bit closer, let's make another scaffolding. And you see this arrow here, let's put this scaffolding in rotation around the black hole. Okay? So the black hole is rotating this way, and the scaffolding is also rotating this way, okay? And now let's repeat the experiment. And what we're going to do is, as soon as we're going to lower in the mass, we're going to release it, and now what he's predicting is that not only do you get mc squared, but you get a little bit more energy due to the fact that you can extract angular energy from the angular momentum of the black hole, okay? And that energy actually is huge. It's a massive number. And people have written, I mean, there are papers out there where people have gone through some of the details of the math of exactly how much energy you would be able to extract from the angular momentum of the black hole. Okay? Now, this led to, yeah? It works out, yeah. I mean, this is sort of a naive way of looking at it. You could just from far away, just drop something in that has some angular momentum contained in it, so it's not falling in along a straight. As long as something doesn't fall in on a straight line, that's essentially the key message. Now, if you go and read his paper, I mean, the explanation is beautiful, and I personally struggle to understand. When you read it, and you say, okay, it kind of makes sense. How does it really work? I mean, there's no maths, there's no formal justification of how this is working. And if the story is true, I mean, based on what Kip Thorne says in his book, I think the idea fascinated but puzzled many people at the time. And it was Zeldovich who came up with this idea of trying to simulate or replace the black hole with just a rotating metallic cylinder. Okay, I'm not sure.
Hey, what are you working on? I'm thinking about how one could use the fact that a rapidly rotating mirror turns virtual photons into real ones as a method of observing dark energy.
It's a pretty cool idea.
Yeah, it's great you're here. I'd love to get an engineer's opinion.
Sure.
This chair is squeaky.
Okay, couldn't resist the temptation, sorry. Okay, so before going to this slide here, what is Sheldon Cooper talking about and how is it related to what I was just saying about a rotating black hole? Okay, the words he said, changing them slightly, is that he wants to figure out how to extract energy by taking a rotating metallic object. Okay, and this was precisely Zeldovich's idea. I won't go too much into the details about it, but essentially what Zeldovich realized, and this was all based on Maxwell's equations, so he's able to now to derive some proper equations that justified this. He said if you've got a metallic cylinder, and this is rotating, okay, and I hit this metallic cylinder, so the idea is that this metallic cylinder must have some absorption alpha, okay, and it's rotating with some frequency capital omega, and I hit this rotating cylinder with some beam that also has some angular momentum, okay? It's light, so the angular momentum has to be quantized. Let's say that let's use characterize this angular momentum with some integer m, okay? So the light is also rotating. It hits the cylinder, it will get scattered off this cylinder, and the question is, what happens, and what Zeldovich realizes that the alpha, actually, when you go in the co-rotating frame, is multiplied by this factor here. This is the optical frequency, angular momentum of the optical beam, rotation frequency of your cylinder, okay? Now you can immediately see from this equation that if this term here becomes larger than this one, this is going to become negative. And what's a negative absorption? It's a gain, okay? So you have a mechanism here. It's really weird. It's completely counterintuitive, and it's beautiful. You take something which is absorbing, you rotate it, and you get gain. Okay? Weird thing, took me ages to understand this. Your input beam also has to have some angular momentum, okay? If there's no angular momentum on the input beam, so this is 0, then you don't get any, you just get pure absorption. Okay, we can come back later on if you want to sort of why that is necessary, if you have questions about that. Okay, so coming back to the original idea though, and by the way, so this idea by Penrose, it is actually what then seeded the whole idea of Hawking radiation in the first place, okay? You can see already, we've got a rotating black hole and someone is saying that a rotating black hole can amplify. You send in a wave, and this wave will be amplified, okay? And then essentially what that then, if you look at what Hawking, if you go from there to what Hawking is looking at, you can see that essentially that's just a distilled down version of this process. It's not the same process. It's a different amplification process, completely different. But that's sort of what seeded this whole discussion in the first place, okay? So what we want to try and do is mimic a rotating black hole in our superfluid. Okay, we need the superfluidity, so we have this Lorentz invariant speed of sound or speed of light. We can easily remember, the flow is given by the gradient of a phase. But we know how to, this is one of the things we can do really well in photonics now. We know how to shape the flow or the phase of a beam. And we can, using SLMs or holograms, we can very easily put a rotating phase, so put OA at what's called orbital angular momentum onto the beam, okay? Essentially as much as we want. And we can also put a radial phase. We need both, remember? We need a radial phase, 1/r phase, to mimic the black hole, the sort of Schwarzschild metric part of this. And then we need the rotation. And so this is sort of the combination of the phase, and this is what a beam actually looks like, okay? You can actually kind of make out a little bit of the twirl here, okay? And then what you have is you can plot out now the speed of sound. It's not uniform. Okay, the speed of sound is changing. Remember, it's proportional to the square root of the density. You can see the density here is changing. It goes to 0 in the middle, okay? And then we have, due to these phases, again, just take the gradient of the phase, and I can plot what my this is my radial phase due to the radial part, and then this is my total velocity, which is just the square root of v theta, the angular velocity squared, plus vr squared. Here is where I have the absolute, so the event horizon, the point of no return. This point here is what is called the ergosphere. It's the point where the flow speed becomes equal to the speed of light. But there's rotation now, okay? In a standard black hole, these 2 points coincide. When the flow speed becomes equal to the speed of light, there's only radial motion, so you get sucked in. When you have rotation, you can now reach a rotation or speed that has the speed of light, but it's still not a point of non-return, because I'm going round at the speed of light. I can still give my object a kick in the radial direction. It will be able to escape from the black hole, okay? But it won't be when it reaches this point. This is the point of absolute non-return when my radial velocity becomes equal to the speed of light. So that's already very interesting. Nobody's ever measured this before. No one's ever measured, forget the astrophysical, but even in the lab, no one's ever measured sort of the splitting of the ergo surface from the ergo region. So the idea of the experiment is you create yourself your rotating black hole, you send in a wave, we've already seen how to do that, and then you look at what comes out at the output. So this is one way that we've been using so far to generate our white and black holes. You can just create a hologram that has the right phase profile, okay? And interestingly, with just one grating, you can get both a black and a white hole because the phases are flipped. So in one case, on one direction, you'll get one diffraction order, you'll get a white hole, and on the other diffraction order, you'll get a black hole, okay? And that's if I just use a square root of r phase, okay? So the gradient will give me 1 over square root of r, and then I can also add OAM to this. And these are sort of very first measurements we performed here. Here you can see the spatial profile of a white hole, okay? Everything's getting thrown out, so I have a hole in the middle. In the case of the black hole, okay, this is something you don't expect to see or won't expect to see in a real black hole, but in these artificial black holes, and everything's flowing in, the light has to go somewhere, right? It can't just disappear, and that's why you see this very large intensity spot in the middle. The light is sort of accumulating in the center, okay? And the horizon is sort of around this region here. And then you can go and measure the flow speed. Remember, the flow speed is just the gradient of a phase, but what's the gradient of the spatial gradient of a phase? It's the k vector, okay? Kz minus omega t. Take the spatial gradient and you get k. So I can easily measure in optics the k content just by going what is called into the Fourier plane of the lens. Okay? If I go at exactly distance f from a lens, I'd have the Fourier transform of my beam. So I can very easily, quickly measure what the k vector content is of my beam as a function of position, okay? And you see this behavior, which is exactly what we're predicting for these black and white holes. So there's no rotation here. Now I've got one with rotation, okay? This is a white hole with rotation. There's a hole in the middle now, both because it's a white hole, but also because I've got a quantized orbital angular momentum. So this is a spatial profile, and the idea, essentially, of the measurements I was showing before is you have an aperture, and I scan it across the beam and measure the k-vector content for every position x of this aperture, okay? And if I do that carefully, I can pull out both, I can measure this component, the ky component, and the kx component, so I can measure the radial and the tangential components and pull out the total v and the radial v, and by measuring the profile of, so that's the red and the blue curves, is the better figure on the next slide, and the black curve is just the square root, here it is, it's essentially the square root of the delta n, which gives me the speed of sound. And where these intersect, it means I've got an ergo region and an event horizon, okay? So this is the same graph enlarged, and you can see here that the total speed sort of intersects the curve over here, and the radial speed intersects my speed of sound over here. So these two lines here identify the fact that I have a clearly separated ergosphere from my horizon, which is precisely what I need in order to go and try and study this Penrose process, okay? So overlaid on top of my hole, these are the positions of the ergosphere and the event horizon. So this is still ongoing work, and I think I want to very briefly move on and show you some other work that we've been doing. But essentially, this is a first sort of preliminary measurement where we have that same rotating black hole. I'm sending in my plane wave now to probe what's going on. And you can see there's all kinds of different things going on here that we can clearly see. Here, the incoming beam has been so strongly redshifted by the gravitational pull that the wavelength has essentially become infinite. And on the other side, it's been compressed. Okay, and I can very, very clearly see this here. And here I can see these. You see here it's relatively smooth, but here there are bumps. And we believe that that is the first evidence of this scattering from the rotating black hole. Okay? And what we need to now do is what we're working on is how do you actually analyze this data and prove that you have black hole superwavelengths. Okay? This is the far field picture. I'm looking at the K vectors. This ring here is my black hole. This here is the plane wave that I'm sending in. And you can see this twirly stuff here. This is the scattered, the new part. This is the scattered wave. In the far field, it's very evident that there's something new that's coming out of this black hole. Okay. Once I've got 15 minutes, oh, ouch. Okay, so I'll go through this very quickly. So this is sort of the last example that I wanted to give you of how you can use optics to create something new and interesting in the lab that's also relevant sort of in the relativistic or in the gravitational context. So what we're doing here is taking, again, our nonlinear Schrodinger equation, and this is the equation that simulates nonlinear propagation of light in a material, okay? And I'm doing something slightly different, so kind of forget everything I've said up till now, and so it's not a fluid anymore. What I'm doing is I'm changing, notice there's not a minus sign here, there's a plus sign. I'm changing the sign of the nonlinearity. In order to do that, I'm just simply changing the material, okay? So I don't have methanol anymore. I have a piece of glass that has a positive dN in dt, okay? So this gives me an attractive potential, but it's also a non-local potential. Remember, it's described, this delta N is given by the heat diffusion profile. It's described by a diffusion equation, okay? These two equations over here are formally identical. I just replace the letters with other letters. So it's exactly the same equation as this set of equations over here. Okay, so I've only changed the letters. But the letters now, if you look, there's M for mass. Okay, there's an H bar, and there's a G, that's big G, gravitational constant. This set of equations here are identical to what are called the Newton-Schrodinger or Schrodinger-Newton. Which order is it? Is it Newton-Schrodinger or Schrodinger-Newton? You like Newton-Schrodinger? Okay. Okay. Let's go with the title of this paper here. Let's just call it Newton-Schrodinger. But anyways, you'll find both versions. But these equations here are identical to Newton-Schrodinger equations. What are they? I think you've already seen this. Is that true? Have someone spoken about this in the previous lectures? Yeah? Okay. So you've already seen this. I don't need to go too much into the background here. But essentially, it's a modified form. Here you have the Schrodinger equation, which describes how your quantum wave function propagates in the presence of a potential, a Newtonian gravitational potential, which is described by this diffusion equation. Okay? They are both, in terms of the physics, what renders these two systems identical is the fact that you have a nonlinear interaction, which is non-local. Okay? Gravitational body affects another gravitational body over here. In this case, a photon or light over here affects what happens to light over here. Okay? Now the question, though, which I don't think was fully addressed in this first paper, was that under which conditions is this analogy actually exact? I mean, is it just some kind of hand-waving analogy, or is it really exact? And it's a relevant question because nowhere am I saying that the shape of this potential is exactly the same shape as this potential. It could be completely different. Okay? And if you're not careful, it turns out that it actually is. So very quickly, so if you want more details, so I've only got 10 minutes, this paper appeared 2 weeks ago. So you can go and read up all the details of what we did in there. But so the first half of the paper is not too dissimilar to the first half of this talk. It's all about sort of trying to nail down the exact non-local, non-linear response of the material, and then identifying how to control it, how to tailor it to make sure that this identification here is exact. And there's an additional complication here, which I want to point out, and it's not trivial, although it might seem trivial. This is a 3D system. It's a 3D equations, x, y, and z, okay, plus time, so 4D if you want 3D plus 1. This is 2D. Notice there's this perp sign here, which this guy doesn't have. This is 2 spatial dimensions and time, okay? So 3D plus 1, 2D plus 1. Why do we care? Well, you care because if you go and look at the response function, so if you go and solve the diffusion equation, okay, and just by taking, for example, going to the Fourier domain, in both cases you'll get a response function in this function of k, which goes as 1 over k squared. Okay. Now, if I do another sort of inverse Fourier transform to figure out what I have in 3D, okay, if I inverse Fourier transform this function in 3D, I get to 1 over r Coulomb-like potential, which is what gravity does. Okay? But if I do it in 2D in my system, okay, I end up with something awful. It's completely unphysical. I end up with this logarithmic function. Okay? So it doesn't decay as 1 over r. This thing sort of diverges, becomes very large as you increase r, but even worse, it can become negative. Okay? So this is in no way even remotely related to this. Okay? So you have a problem. So if you just take this face value and say, this is what it is, or isn't this fantastic? Well, actually it isn't. It's really bad. You can't just say, oh, this is going to be a 2D slice of this. It's not, okay? It's just wrong. So you have to do something in order to tailor the response here, in order to sort of harness this 2D nonlinearity to really make it behave like 1 over r Coulomb-like potential. So the trick here, again, goes through sort of, we use the same distributed loss model that I mentioned earlier on to just study analytically what our heat sort of diffusion function is doing. Remember, through the distribution, this loss model that I showed you earlier on, we have this kind of dependence for our. So essentially what I'm saying is, the problem here, why do we have all these weird behaviors, is because when we solve this, we are not including the boundary conditions. Okay? So let's do that. You want to include the boundary conditions. If you do that through the distributed loss model, you end up with this function. Okay? And now, indeed, if I take a Fourier transform of this guy, it is actually well behaved in the direct space. Okay? It is this K0 function, which fortunately is never negative, and it's exponentially decaying. Okay? But it's still not the 1 over r Coulomb-like potential that I'd really like to see. Okay? But what you can show is that in the limit where sigma k is squared, or sigma k is much larger than 1, you can see here, if this is much larger than this term, I can throw this away, and so my response function becomes once more like the gravitational response function. That's the first step. Now I need to check that the correspondence works in K and direct space. Okay? And also, and let's take one step further, the other thing I can show is that you can see is that when in this limit, so for example, what does that physically correspond to, by the way? It corresponds to taking something like a donut beam, for example. Okay? Sigma k, or essentially k much greater than 1, means that all the on-axis components have been put to 0. Okay? So a beam, a ring-shaped beam, for example, will give me this kind of k distribution when I go into the Fourier domain. So essentially it means that there is an exact, and you can also show that when you have this, that this function here does indeed behave like 1 over r when I take this limit. Okay? So essentially what I'm saying is that when this is true, then you have an exact correspondence between a 3D gravitational object that looks like this and this system where essentially I'm taking this sort of this line out, an equatorial plane, if you want, of this object. So I have this sort of like ring-shaped beam. Okay? So you have to be careful. This model is not universally valid. If you really want an identical sort of identity with the Newton-Schrodinger equation, then you have to make a very specific choice of the kind of objects that you want to simulate. Okay? So again, you've already seen these measurements. I don't need to go through them again. The setup is essentially identical to before. You have a laser, an attenuator, you have your phase mask, your hologram. You select out one of the diffracted orders, and now you go through this very long piece of lead glass, which is what is giving me the non-local nonlinearity. Okay? And these are just measurements showing that we indeed we know exactly what the non-local length is. Okay? So the idea we came up with, so what object can we find that does actually have this kind of just naturally displays this kind of behavior, this kind of shape? And the answer is, for example, there's a class of stars out there called Boson stars that do behave like this. So the Boson star, or there are also BC stars, the various sort of ways of describing this. But essentially, a cloud of bosons or BC star is described as all BCs by sort of quantized by quantum wave function, or what is often called an order parameter. Okay? And you can write out an Einstein-Klein-Gordon equation that describes the evolution of this wave function. Okay? And it predicts a stable solution. So the gravitational, it means that it can form a star. So under the force of gravity, it will form some kind of spherical object. Okay? Where the gravitational collapse is counterbalanced. The word you'll find in literature is dispersion, which confused me for a while, but essentially it's just a terminology thing. It's the Heisenberg uncertainty. Okay? As this thing collapses under gravitational force, at a certain point you'll be trying to localize it so that the delta x times delta p condition greater than h bar starts to come into play. So as it collapses, delta x becomes smaller, so the uncertainty in the momentum becomes larger, which will tend to spread the star back out. Okay? So that's the counteracting mechanism for gravitational collapse in boson stars. Now, the key point is that in the weak field limits, that means for very weak gravity, you can actually, it's relatively simple to show that the Einstein-Klein-Gordon equation reduces exactly to the Newton-Schrodinger equation. Okay? So although this equation was introduced by Penrose to study gravitationally induced collapse of a quantum wave function, it does also naturally emerge as the weak field limit of the Einstein-Klein-Gordon equation. Okay, so different ways of deriving this equation. Boson stars are candidates for dark matter, for example. They're also very often used as models for modeling neutron stars. People believe that there's a large component in neutron stars that is composed of a BC or a superfluid. Okay? And some believe that there might be an alternative explanation to at least some of the black hole objects that we can observe out there. If you're more interested, if you're interested in this, have a look at this review paper. So experiments, these are experiments of our boson star. I'll quickly go through this. Essentially, this is a line out. So there's a ring here. I'm just seeing the transverse profile. And this is input power, but I should read it as I show in the numerical simulations. It's essentially propagation distance or time. And I can see that the boson star evolves by essentially bouncing back and forth. Okay? I forgot to mention that I'm not just taking any boson star. Remember, I have to have a hole in the middle. So what we're doing is we're taking a rotating boson star. Okay? And the boson star BC has an order parameter. It's also quantized, so it has to have quantized angular momentum, just like our optical. Okay? So it has to have a hole in the middle. Zero intensity, because there the phase is undefined. And this is the trick with which we force our beam at all times. You can see at all times here, there is nothing on axis. And indeed, if you go and look at the sigma K spectrum, you can see that at all times on axis, our sigma k is always larger than roughly about 20 in these units here. So sigma k squared is of the order 400. It's always much greater than 1. Okay, and this is, I mean, of interest. There are lots of papers out there in boson stars trying to perform numerical simulations and see what these things do. And it's sort of known that these things bounce around. Right? So here's the numerical simulation where you can see the collapse and you can see it moving out. And here you see the phase spiraling around. Now there's a detail here. You see these two humps. You can see the two humps rotating around. This wasn't a mistake. We put that there on purpose in the simulation because that is also what we had in the experiment. And there's some very interesting behavior here, which we're still looking into. And this falls more under sort of the domain of, there's a new sort of vogue at the moment going on. People talking about quantum droplets. Okay? So people have observed these quantum droplets in BEC. Essentially, this is another form of quantum droplet. And this dynamics are dynamics of a quantum droplet moving around. Let me show you another video where it looks more obvious that this is indeed behaving like a droplet. You see how it's bouncing around? Okay. So what we're doing now is studying this in terms of a quantum droplet, which is moving around in this rotating potential. So I don't have time to go into the details of that, and I think I'll stop here by simply saying that, so all this, I think it's fascinating physics. The beauty of all this is that the experimental layout is something that with, you only need $10,000 or pounds or whatever currency you use to build this setup. The setup is extremely simple. The physics is not, which I think is really what makes it beautiful. You don't need to get distracted by the technicalities of the setup. You can really sit down and think about the physics, and there's lots of physics. We went from the heat diffusion equation to rotating black holes, to Newton-Schrodinger equations. We're now talking about quantum droplets. I mean, take your pick. There's a bit of everything for everyone in there. Superfluidity, okay? And what we want to do now is we want to actually go back to original Penrose idea, and this is actually an open question. Can we study wave function collapse? And I'm being purposely vague here about what I mean by wave function. But can we study wave function collapse using our Newton-Schrodinger equation? That's it, so thank you. Yeah, question? Mm-hmm. Here I'm less interested in the dispersion. In the Newton-Schrodinger equation, it's not written anywhere that I have to have a linear dispersion. So the linear dispersion, I'm not sure it even makes sense to talk about a linear dispersion here. Because remember, so this is a very, so something else I should point out about the Newton-Schrodinger equation model, which is very exciting. There's a big difference compared to the first, two big differences compared to the first half of the talk. This is not a fluid, okay? In order to talk about a dispersion relation, I need a fluid on top of which some waves can propagate. If I don't have that, you don't have waves, then I don't have a fluid, I can't define a flow speed, I can't even define what a wave is propagating on a fluid that doesn't exist, so it doesn't really make any sense to even worry about whether there's a dispersion relation or not. But the other key difference here is that this is a fully nonlinear system, okay? So all other analog models to date, not only were they 1D, this is now 2D, but they were also always looking, think of Einstein's equations, right? They're fully nonlinear. We mentioned this, I think, yesterday. You have your stress energy tensor term on the right-hand side, which modifies the space-time, which modifies the mass distribution, and so on, okay? But what the whole point of analog gravity is to study the kinematics, though. So you assume that the space-time is fixed, and then you study what how a test particle moves inside the geometry defined by your space-time, okay? It's not modifying the space-time itself, never, okay? So you're completely losing that nonlinearity, that back reaction that feeds that good sort of loop. Here, okay, we don't have small waves propagating on top of something. We have an object which is defining its own, I don't want to use the word space-time metric because this is not GR, this is Newtonian gravity, but it's defining, if you want, its own geometry. It's defining, it's creating its own mass, and then it's evolving under the effect of its own field, and that in turn is changing the field, which then in turn changes the mass distribution, and so on. So you've regained the full nonlinearity of the gravitational dynamics. This is the first time this has ever been done before, okay? We have lost something, of course, in the process. We are not at the GR level anymore. We've gone into the weak field limits, and we're at the Newtonian level. So I guess there's one big piece missing in the puzzle. Is there an analog system out there that can capture the full nonlinearity of the full GR system? So at the moment, we've got sort of part of that answer, but I think that's a key point here. But there's no nonlinearity, right? I mean, there is, but it's extremely weak. It's not.
So the discussion is really interesting, and I love to hear more. In viewers' time, I propose that we cut it here. Okay. So let's thank Professor Faccio for his set of lectures.
Thank you.